We're going to continue our discussion on CFD, and I'm going to do a demo today. I know I started some of this in class already, but so that this is complete, I'm just going to start here at the beginning and say some of the things we already did. Okay, so last time, or in the homework, as you've been working on CFD simulations, we've been doing inviscid flow, and on the left you see an appropriate inviscid mesh. Because there is no viscosity, we don't need to resolve the boundary layer. But as we started discussing in class, for a viscous solution, we do need to resolve the boundary layer, and we normally do this by what are called Prism layers. Depending on the software you use, they'll be called different names, maybe boundary layer elements or prismatic elements, but they have this same idea where an unstructured mesh all the way to the body is not very effective. There are a few reasons for that. One is, in the boundary layer, as we've discussed, flow properties are changing much more quickly normal to the body than they are along the body. And so we want to use, for efficiency, high aspect ratio cells. As you can see here in this little insert picture, the cells are very high aspect ratio, stretched in one direction where things are not changing very rapidly. We also need, and as you can see in the picture, very small cells. We talked about what Y plus value means and sort of the law of the wall. And to get a good resolution of our mesh, you want to go down to a Y plus of 1, which is very small. And so we need to do this efficiently. A structured mesh is going to be more effective. A third reason to use these prism cells is that we can align the cells. This is a structured mesh, align them with the body. And because they're aligned with the flow, we have less numerical diffusion than you would with just a regular unstructured mesh. Okay, and so maintain that structured mesh everywhere is very difficult, so generally we create this region. Again, in StarCCM it's called prism layers, and as you see in the picture, we have a transition from prism layers to the unstructured mesh on the outside. In case I forget, I'm going to say this now, but an important thing to note when you're creating these layers is not just to make sure you have a good prism layer, but to make sure that the external mesh transitions very nicely with the boundary layer mesh. So in other words, you don't want a large jump in cell size. I don't know if, I guess my mouse isn't visible, as you go from the last cell in the boundary layer to the first cell in the unstructured mesh. That's a common problem that I see. Okay, so we're going to talk about how do we size our prism layers. Of course, we could use just a general grid convergence study, and we still need to do that, but we can rationally size the cells in our prism layer and avoid having to do a separate convergence study for the prism layer for the most part. So how do we do that? Well, first, we need to select the overall height of our prism cells, and what we want to do is to encompass the whole boundary layer. An obvious way to do that is to use our flat plate formulas for, say, boundary layer thickness. And this is a formula we've seen already. Here I'm using the turbulent Schlichting formula for boundary layer height. And instead of using delta, I'm just using a big T. I'll use that because it'll be, I think, a little easier to see in the formulas later, but just same formula we've already seen, just a new name. Of course, the geometry that we're doing is not a flat plate, and we don't actually know the local Reynolds numbers, but this will give us a good approximation of how big our boundary layer is going to be, just based on the free stream velocity and the body length, the characteristic body length of our geometry. Okay, so that one's pretty straightforward. The next thing is to choose the size of the first cell, meaning the cell that's closest to the body. And as we've discussed in turbulence theory, if we want to have a good resolution of the boundary layer, we need to go all the way down to a Y plus of 1. Here I've written again what the definition of Y plus is. So we want to choose that first Y such that this is true, right? That Y times U tau over nu is equal to 1. That's the right size that we want. So if we solve this for Y, this is the expression we get. Okay. I'd like to, and we can use this directly, but I'd like to do some mathematical simplifications here to see what parameters we really need. So let's write down first what the definition of the friction velocity is. It's the square root of our shear stress over the density. And now let's use the definition of the skin friction coefficient and plug that in place of tau. Okay, when we do that, we see that rho is going to cancel. So in other words, we didn't really need to know rho offhand, right? So even before setting up our simulation, we may want to make an estimate for these things. And so there isn't actually a direct dependence of rho here, although there is implicitly in the Reynolds number, as we'll see. And so now let's solve this for VE, okay? Or sorry, not solve it for VE. Let's just simplify it. So the VE comes out of the square root because it's squared. And now we have VE times CF over 2. And I'm going to plug that whole expression, this expression for U tau, up above. And if I do that, now I have this estimate for Y, which is nu over the edge velocity times that quantity in the square root. Okay, but we can do a little more. I'd actually like to start bringing this to Reynolds number because that's something we should know. That's a non-dimensional number. That's a macro level feature of our flow. And so let's keep going. Reynolds number, or at least the local I'm sort of mixing syntax here. VE is the local velocity, whereas L is the body length. But for our purposes, we'll generally have to use the free stream velocity because we don't actually know the edge velocity yet. We haven't done a CFD simulation yet. We're just trying to estimate how big we need to make our prism layers. We can solve this for VE or nu. Either way, what I'm going to do is try to plug it back in the expression above. So here I've solved it for VE, and I'm going to plug that in to my expression up above for Y, and this is what I get. And I changed Y, this generic Y, to T, and this little t is going to mean the distance to the first cell. So big T is the distance to the last cell in my boundary layer. Little t is the distance to that first cell. And then one piece that's missing, of course, we need the skin friction coefficient. So again, use the turbulent empirical formula from Schlichting. And we could use the laminar ones, but you know, in general, most of our flows can be turbulent, and be conservative to use a turbulent boundary layer estimate. Okay, so there we have it. We've reduced this process down to an equation that only depends on knowing the Reynolds number and a length scale. So again, this will be the length scale of the body. Really, it's the length of the boundary layer, but some length scale of the body. And then the Reynolds number, we would use a free stream Reynolds number. Okay, so with just a couple pieces of information, we can have a really good estimate of the overall height of the boundary layer and the distance to the first cell in the boundary layer. So now we need to figure out how many cells we put in between the boundary layer, or in the total boundary layer. The default and method in StarCCM, and there are different methods for doing this. So you know, this isn't necessarily a general formula, but mostly something similar. And you can look up what it is for whatever CFD package you're using. But a very typical method is called geometric progression, and this is the formula for it. So again, big T is the height of the whole boundary layer. Little t is the first cell. S is the stretching ratio, or the growth rate. So in other words, each cell is going to be a little bit further away from the last. And then N is the number of cells in the boundary layer. So we want to know N, and to me the more fundamental parameter here is, oh, sorry, I have to escape this because it's, oops. Okay, let's go back real quick. The growth rate I can usually specify a priori. I can say, well, I want a growth rate of, say, 1.2. That would be a value that I like to use. I think the default is more like 1.5 or something, but I think that's a bit aggressive. And I want to solve this for N. Conversely, I could pick N, but that's really hard to choose. What's the appropriate N? It's easier for me to choose an appropriate growth rate. So I want to solve this equation for N. That's done easily enough, and here's the expression. We already have big T, little t, and I choose S. Like I said, something like 1.2 is something I like to use. And now we can solve for the number of cells in the boundary layer. All right, so let's use that. Let's go back over here to StarCCM. Turn this off. Okay. So I've opened up the simulation from the last video, the Inviscid one. I haven't changed anything. I've just opened it up, the same one that we saved last time, because I'm going to do that same airfoil. It's a NACA 2412. Right now it's set up at 5 degrees angle of attack. We already did a grid convergence study, at least for the Inviscid flow. So I've got a pretty good starting point to move into a viscous simulation. And I just want to focus here on the changes I need to make to handle a viscous case, rather than starting from scratch again. If you need to remember some of those steps, so you can go back and look at it. So we've already got our geometry. I don't need to do anything that. We've already have our parts and regions. We have a mesh, but we're going to need to change that mesh, obviously, so we can add the prism layers. So I'm going to right-click here on the automated mesh and select meshers. The last time we did it, we only select the polygonal mesher and did not select prism layers, but now I'm going to select that as well. Okay, so now I've got that as an option. And if I look at my meshers, I've got the polygonal, here I've got the prism layer mesher, and you can see here the stretching function, geometric progression we just talked about. There's another option here, hyperbolic tangent, but the default here is geometric progression, and we're going to use that. So if I look under here under default controls, all of these we've set already in the past. Base size, proximity, growth rate, things like that. I picked, or these target surface sizes, I picked last time, and we did a grid convergence study to help choose good values. But now I need to figure out, or I need to specify the prism layer. So you can see I have a few new parameters here. So I did those 3 calculations already beforehand for the Reynolds number I want to simulate at. I'm going to do a Reynolds number of 5.7 million. The reason for that is because I have some experimental data that I want to compare to at that Reynolds number. So I did the same calculations we just looked at in that little presentation, and it turned out I got 35.8 for the number of cells, so I'm going to put 36 here. Stretching, the default is 1.5, but I like 1.2, something less aggressive. And then I need one more parameter here, total thickness, and I don't want to do it relative to base, because then I'm going to have to do some calculation to figure out what fraction that is. I know the actual size. Again, I did the calculation. This would be big T from that previous calculation, and it was 0.0165. Okay. Now I'm going to go look at these custom controls. One thing I'm going to want to do is right now this is going to want to put a prism layer everywhere, because everything is going to inherit that. This surface control is for my inlet and outlet. You'll remember we wanted to put some different sizes there. So I'm going to go here to prism layers for that. And I don't want it to take the parent. I want to disable it so it doesn't try and put prism layers on the outer boundary. Curve, that's not a problem. It's just going to be on the surfaces, or more on the surfaces that'll happen. Okay, so what else do I want to do? I'm just going to let that run while I look at this. So here I have a curve control, and what I did is I was putting a few more cells towards the leading edge and the trailing edge. That's actually going to kind of mess up my mesh, because it's going to interfere with what I'm doing in the boundary layer. I don't need that. So I'm going to get rid of this, actually. I'm just going to delete it entirely. Maybe I can show you that first before I do that. Let's go to Scenes, Mesh Scene. No, it doesn't look too bad. Actually, that looks okay. So let me just say a few things here. The trailing edge is going to be a little messed up, though, because of that. Here's the prism layers. And if I zoom in a lot, I mean, you can see I'm resolving way down, right down to Y+. Like these cells, they're actually getting a little bit ridiculous in terms of the aspect ratio. I don't think that's good. So I'm actually going to refine these cells. I'm going to change my base size and divide it by 2 so that this gets divided in half. I did a convergence study in Viscid, but of course that maybe not good enough for the Viscous solver. You can see as I go out, the cells get bigger and bigger. That's the growth rate, so they're growing by a factor of 1.2. And then finally they reach here, big T at the edge. And these cells, they're okay. They're pretty well matched, so that's pretty good. Okay, so The other thing that's common with a viscous, yeah, let me just look at the trailing edge. This is going to be a little messed up because it's trying to create this boundary layer. It's not actually that bad, but I'm just going to get rid of it. No, maybe I don't need to. We'll see. I'm going to add an additional custom control here because I want to add a wake refinement. I don't want to do it here because this is on the leading and trailing edge, and I don't want to put a wake refinement on both sides. That won't make as much sense. So I'm going to add a new curve control here. I'm going to select the trailing edge. And let's see, target surface size. What I want to do, I'm just going to leave that as is because that's already being controlled by this one. Wake refinement. Okay, so I'm going to select that. Okay, so wake refinement. First it's going to ask how far do I want to go. So this really depends on what you're trying to do. In my case, all I want is the forces, lift and drag, pitching moment. So I actually probably don't really even need to do any wake refinement, but I'm going to go one body length back. That's probably sufficient. And my body length is 1. The chord length is 1 meter, so I'm going to put this as 1. That means I'm going to add some additional refinement here. If I was trying to do a wake resolution study, this would be important, but the wake, after about 1 body length, isn't going to have a huge or that much of an influence on the forces, and that's all I care about in this particular study, so I'm not going to go too far. Direction, so often it's nice to align that with your angle of attack, but I'm not too worried here, so I'm just going to keep that straight back, and I may want to do multiple angles, so it might be convenient to leave that or to change that programmatically. Spread angle, I don't know, let's see, I'll probably want to do about 20 degrees. I'm just going to calculate real quick. I think that's about 0.3. That may be a lot. That's 0.35. So I'm going to do, let's say 0.3 radians. I think that's going to be plenty. Okay. Now the relative size, percentage of base. What have I done on the body? I think I have the relative size. Target surface size is 1%, so I don't really need to go that far. I'm going to try 5%, see what that looks like. And then growth rate of the wake, that's probably okay. I'm going to let this run. This is going to take a little bit longer than the first one to run because the wake refinement just takes longer, even though I didn't really put that big of a wake. So while that's going, I actually don't think it should take too long, but let's take a chance here to look at some of the documentation. So here I'm at the documentation for StarCCM, looking at the best practices guide. Same one we looked at before. I just want to make sure we're doing things consistently. This is external aerodynamics, steady state RANs. That's what we're doing. Okay, and so these things are the same as before, segregated flow, constant density. I'm going to have to pick some models pretty soon. So I'm going to set this as turbulent. I'm going to use the RANs. That's going to be selected automatically if I pick turbulent. And then it recommends as the turbulence model, either the realizable K-epsilon model or the Splart Almaris model. It prefers the K-epsilon, and we talked about some of the reasons why this is preferred, especially if you've got a blunt body, in other words, separation. Splart Almaris model works well for streamlined geometries, attached boundary layers, mildly separated flow. That's really our case. I actually have tested both of these on this problem, and the differences is very small, so it won't actually matter too much for our case which one we use. Mesh settings. Let's see, let's just say we got to refine wakes, leading edges. Yes, so we've done these kind of things. Talks about some advantages of polyhedral meshes. Okay, prism layers. So there is something called a wall function, and I'm going to show you what that is in a minute. If you care about drag, which I do in this case, especially getting skin friction drag, then we need to integrate to the wall, and it says we need to go to a near wall y plus being about 1, and that generally means you probably have about 20 to 30 prism layers. In our case, we had 36. You You can use something like a wall function. I'll show you what that is. That means you don't actually go all the way to the wall. You go to a wall y plus of around, say, 50, which is in the log region, as we talked about. And you would do that if you need to save computational costs. It's not going to be as accurate if you care about drag, but if you just need sort of a general viscous behavior and you care more about, say, large eddies and wake behavior, that might be okay to do. But for aerodynamics, often we care about drag, so we almost always, want to resolve down to y plus a 1. Okay, so that's sort of best practices guide. The other thing I'm going to look at, here I'm in the documentation, going to simulated physics. Let's look at modeling turbulence here. So there, it's going to talk about models that provide closure to the Rand's equations. We've already discussed why we need that, and it's also going to talk about for LES and DES what you would do. So first we need to select a turbulence model. We're going to see this in a minute. For Rands, these are going to be the 4 options we're going to have, and we talked about 4 of these: the K epsilon, K omega. K omega is generally better in a wall region. I think Taylor asked about the SST, and I believe what that does is a hybrid where it uses K omega near the wall and K epsilon further away. Splar-Talmaris, good for aerodynamic applications with little to no separation. And then the Reynolds stress turbulence, which isn't, I don't use as much, but that would try to model each term in the Reynolds stress separately, so it's much more computationally intensive. And actually, let's read about some of these things. Here it says Rand's turbulence models, and let's see what they recommend. This kind of stuff should look familiar. It's showing you, okay, we took the Navier-Stokes equations, divided everything, or split everything into a mean and a fluctuating component, and then we got this new term, right, the Reynolds stress tensor. And many of these models, all of them except for that Reynolds stress, the one where it tries to model each individually, the Reynolds stress transport model, is going to use, or all the others use this Boussinesq approximation. I didn't show you this part because we were assuming incompressible, but what you can see is it's exactly the same model form as the regular stress tensor. We've just replaced the normal viscosity, or viscous viscosity, with this eddy viscosity. Okay, so deciding on a Rand's turbulent model. Let's look at that, and wow, this mesh is taking a while. This should follow things we've kind of talked about. The SA model is good when things are largely attached, very mild separation. K epsilon, this is sort of your general all-around model, fairly robust. K omega is very similar. It works better in sort of wall regions. And the Reynolds stress transport is the most complex. It's recommended where turbulence is strongly anisotropic, such as the swirling flow here. Okay, so we've already discussed these things. The other thing I want to talk about are 2 things we didn't talk about in class. One is this wall treatment. So this picture should look quite familiar to you, something like this. We talked about the viscous sublayer region, right, and this log layer region. So normally, if we care about drag, we want to use what's called a low y plus treatment, meaning we're going to resolve all the way down to y plus equals 1, and that's what we're doing here. There are some alternatives though, because as we discussed in class, this behavior is quite universal. If we normalize properly, we can model that, and so you can just resolve down to the log layer, somewhere around 30 or 50 or so, and then a model will be used to or modeling this inner region of the boundary layer. Again, this is going to be less accurate if you care about getting the wall shear stress, or in other words, the skin friction drag correctly. So I have not used it, but there may be cases where you would want to do that. The last thing we didn't really talk about was transition. So you may not have caught this, but when we are talking about turbulence models and Rands, right, the assumption there is that it is turbulent, like fully turbulent everywhere. There is no laminar flow. Alternative, we could assume everything is laminar, in which case we can solve the Navier-Stokes equations directly because there aren't so many scales. Laminar flows are self-similar. But if we, so generally when we do RANs and we have a turbulence model, everything is turbulent from leading edge all the way through. And that's the most common case. Our measure is almost done here. There has been some development though on transition models, but there are only a few turbulence models that they will work with. I think actually all of these only work with the K omega model. So if you choose any of the others, there's no option for transition. They can't handle that, but the K omega model can do transition. And there are three options here. The first is the easiest, or I should say the simplest. And what it does is kind of a bit of a hack here where it says we're just going to turn turbulence on or off. And it's not a model. You have to tell it to where that's going to happen. So beforehand, you have to say, like, here is the region where there's no turbulence. Say you were modeling, like, this is where the boundary layers can be tripped. And this is the region where I want you to turn turbulence on. So in this region, it's just going to turn off all those turbulence terms, and then in this region, it'll turn them back on. So this is useful if you happen to know where turbulence is going to transition, like say you were comparing to a wind tunnel study and you had a boundary layer trip on there, so you knew where that was going to happen, then this would work well. If you wanted to predict it, there's this model called the gamma RE theta. It means there's two equations here. RE theta is the Reynolds number based on momentum thickness that we've seen. This gamma is what's called this intermittency factor. So it's trying to predict sort of when turbulence is starting. It's sort of like a, I guess if it's 0, there's no turbulence. 1 is full turbulence, but transition is not, even though we've sometimes modeled this way, it's not a discrete event. So it's trying to calculate when that happens. It's this 2-equation model. I've actually never used these before, but I did just to test this out, and it worked quite well. So I'm going to show you this today. And there's a simpler one, the gamma transition model. And this is the one I'm going to use. It's a little faster. And you can go in and read more about these if you'd like. But again, these don't work for all turbulence models as far as I know, and the ones for RANs, it's only the K epsilon, or sorry, the K omega model, but these will work. Okay, so our mesh completed. Wow, that was way more cells here in the trailing edge than I wanted, but I don't really want to run that again, so I'm going to leave it. Boundary layer looks pretty good. I've got good resolution. Actually, you know, I am going to have to run it again, but I may not do that. Yeah, see, this is what I'm talking about. It's kind of messing things up by, it's trying to resolve this wake region, but it's also trying to, it's conflicting with this curve control I had from my Inviscid simulation. So, boy, I don't know if I really want to run this again, but I may have to do that anyway. Okay, so I'm going to delete this. Actually, you know what? I am not going to delete it. I'm just going to take off the trailing edge portion of it, leave the leading edge one. And yeah, that refinement in the wake is probably more than I care, especially because I'm going to take down the base size. So what did I do? I did 5% of the base. I'm going to have the base size, so that's going to be equivalent to 10%. I'm sorry, too. Yeah, I'm just going to, let's say, well, I'll just leave it at 10. That's okay. We'll keep it at 10. But I'm going to take the base size down by half because I think I'm going to need more resolution to get a good drag value. Okay, so I'm going to let the mesh run. Hopefully it won't take as long without this conflict, but it's still going to take a couple minutes. If I have to, I'll just cut this part out. Okay, so it's quite normal to have to mesh multiple times, but let's see if it'll let me do this while this is running. I'm not sure it will. Yeah, it's not going to let me do it. So I can't change my physics model. So the next thing we're going to have to do is to turn on, well, we're solving Inviscid, so we're going to have to turn on the Viscous model, add turbulence. Let's see if I can change my initial conditions and things like that. That I should be able to do. So we can do something while we're waiting. Okay, here we go. So I'm going to change my velocity. I right now have it set at 10, and I did that just arbitrarily. It didn't matter because I was doing an inviscid. I just normalized everything. But now I need to get the right Reynolds number. So first I need to know the density and the viscosity. I haven't turned on the turbulence, so it's not going to show me viscosity, but I know what the default is. So I'm going to just use it. Here's the density, 1.8415. I could change that. I can make it whenever I want. I'm going to leave it as default. Once I turn on viscosity, there's going to be a second term here for viscosity, and I know what that number is. So with those two pieces of information and the chord length, I can compute the velocity I need to get the Reynolds number that I want. And in this case, that velocity I already calculated beforehand, and it's going to be 89.3 meters per second. So this will give me the Reynolds number that I want. Okay, what else do I need to do? I'm going to need to run for a while, so I'm going to change my stopping criteria. I'm at 8,000. I'm probably going to have to run this for a while. I'm just going to set this up to 12,000. I don't think it'll actually take that long, but let's do that. And what else? Anything else I need to change? I think that's really it. As you'll see, once I turn on viscosity, there'll actually be a few new things I can specify on the boundary. Turbulence intensity or the eddy viscosity ratio. I'm going to leave those all default, sort of a typical turbulence level, but if you want to change, have a higher turbulent inflow or lower turbulent inflow, those are things that you can change. What else can I do while I'm waiting? I'm going to create a new scene here. Scalar scene. And what I'm going to do is I want to look at the y plus value because we made these estimates on what boundary layer resolution I need, but I need to verify that these are actually giving me what I want, and so I need to plot the y plus values on the surface so I can see that I actually have something that's in the neighborhood of 1. I guess it's not going to let me do that until it's finished with the wake. Anything else I need to do? I'm going to start opening these plots because I'm going to want to look at them. Lift, drag, these are the same monitors from before. And I'm going to need the reports because I'm going to extract those values. And now we just have to wait for the mesh to finish. Okay, the mesh finished. Let's take a look. The leading edge looks good. I'm glad I left that refinement so I can get extra refinement here around the front. Because I actually probably want even more there, but that's okay. That's okay for now. For this demo, trailing edge looks better. These cells are maybe bigger than I would like them to be. I'd have to do a grid convergence study to see how fine they need to be, but point here is you can see what the wake is doing. It's hard to see unless I zoom out. You can see it's acting over about or across one body length. It has this spreading angle of about 0.3 radians, which is probably quite generous. So you can see what that does there. Okay, so we've got the mesh. This is going to be, I think, good enough to go. Okay, now we need to actually make this no longer inviscid. So I'm going to go back and select models. I'm going to uncheck inviscid. Everything else is going to be fine. Notice I can choose either laminar or turbulent, not both, right? If I select turbulent, which I'm going to do, it's going to automatically select RANs because you can see it automatically selected that. That's the only option. Now I've got 4 turbulence models I can use. I'm just going to use the Splar-Talmares because it'll be appropriate and is the simplest for this case. And it automatically selected that I need to use an all Y plus wall treatment for this case, meaning I need to go down to Y plus 1 for the types of models I've selected. Some of the others will give you an option to get, like I said, that low wall Y plus. Okay, so some new things appeared up here. Dynamic viscosity, right? Said I knew what that value was, and yes, that is the value I'm using. So that's in my physics model. Now for inlet conditions, I have a new thing here, turbulence. I can specify turbulence viscosity ratio. I could change it to specify other things, diffusivity or an intensity and length scale. Like I said, I'm just going to leave this at its default viscosity ratio of 10. Velocity I already set for my Reynolds number. This is already at 5 degrees angle of attack. So all of that is good. I changed my stopping criteria, so I should be able to start running this. Okay, so I'm going to start letting it run. This scalar scene popped up, so I'm going to right-click this and choose wall Y+. Okay, and right now it's not going to really show me anything. This is only defined at the wall. So what I'm going to need to do is I need to go into that scalar scene right here. It's number 2. Let's see, I think attributes. No, let's see. Yeah, displayers, sorry. Let's go into the scalar and select what parts this is going to show on. Right now it's trying to show it in the region. That's not going to work. I need to show it. I could either do the I'm going to pick the airfoil here. And unselect the region. Okay. All right, so it's showing me the Y plus value on my airfoil or at the wall. This is only defined right at the wall, so it only really makes sense here. You can see, I mean, this isn't converged, obviously, but you know, this is looking good. Everything is close to 1 or below. So I may have even gone too far, or farther than I need to, rather. So why is it much bigger here? Well, you'll recall that skin friction, or the skin friction coefficient, is much higher at the leading edge, and it tapers off towards the trailing edge. And if we go back and look at our definition for Y plus, right, it has the skin, or the friction velocity in the numerator, which is proportional to our skin friction, our shear stress, which of course is proportional to the skin friction coefficient. So because that's here in the numerator, Y plus is going to be much bigger where that skin friction is really high, or the shear stress is really high. It's still rising, but I'm, you know, in the neighborhood of 1, so this is looking pretty good. My residuals are coming down. Let's take a look at, I'm going to have to adjust these monitors. So my drag went up quite a bit from where it was in Viscous, right? It was like at 0. That's where it should have been at least. And the lift is also, I mean, that's partly why it went up. The other part, of course, my lift should be dropping, but the reason why lift is going up is because I changed my velocity by a lot, right? It was at 10 meters per second, and now I'm almost at 90, so my dynamic pressure has gone up by 90 squared. What is that, like over 8,000? So I'm going to adjust the scales of these plots. The lift is still climbing, and so that's going to auto adjust fine, but drag, you know, had this spike. I don't really need that, so I'm going to cap this at 100. So let's go to my drag plot here. If I go down to axes, expand that, the left axis, the max I'm going to put 100, just so I can zoom in a little bit and check to see that this looks like it's converging. Okay, so it's not there, obviously. This is still going to take a little bit of time. I guess I can open up my other scalar scene. I think I have a pressure. Yep, it's a pressure field. I'm going to look at other fun things. Let's look at the turbulent viscosity. That's pretty cool. How about, what else do you want to look at? Well, There are lots of things. Actually, you can create a lot more. There's we'll show this in a future video perhaps. You can create custom calculations, but there's quite a bit of things here. I'm just going to go back to pressure. And let's see how close we're getting. Looks like we're starting to get closer to leveling out, at least on the residuals. But let's check the lift and drag. Drag is still not leveled out. That's going to be the hardest to converge. And the lift is still climbing quite a bit, so we're still going to have to wait a little bit. Actually, I'm just going to keep going because I've already run this. We'll let this run. I ran this for this case that I've shown. It wasn't the exact mesh here because I can't remember exactly what numbers I put in, but it was very close to this. And I ran it again with a different turbulence model. And I'll show you that after this runs because I don't think it's going to let me change it while things are going. Actually, it might. No, it won't. Okay, so I'm going to come over here. I went, downloaded this PDF online. This is a very famous data set from NASA. Let's see what page I'm on, 138. This appears actually in several books, many of these data points from Abaddon on Donhoff. Let's see, now I just can't remember what page I was on anymore. I have to search. 2412. Okay, here we go. So I'm running the NAC at 2412. And if I zoom in here, you can see this Reynolds number 5.7 is one of the data points. It also appears here. I picked this one because it has two data points. The one here, this is just free transition, right? So it's going to be partially laminar, partially turbulent, and that's the squares here. And then it ran a second time where it's being tripped to the leading edge, so it's fully turbulent. And there are two cases for me to compare to, and this is why I wanted to show both. So the current case I'm running with the Splart Almaris, this is assuming fully turbulent, so it's comparable to this case. The second scenario, I would need to use transition, and to do that, I have to use the K omega model, and I chose the gamma transition model. And so I did that beforehand, and then I pulled all these plots, or these points from the plot. I used a tool online called the Web Plot Digitizer. It makes it pretty easy to grab these data points. I did that for a lift here and drag. I should have done moment, but I don't think I did that. Okay, and so these were the numbers I got for those two cases for lift and drag. I've put in the density, viscosity. I don't really need that Reynolds number anymore. From StarCCM and the velocity I ran at, and I'm normalizing lift and drag. Here's the angle of attack in degrees I'm running at. And so now I'm going to plot these against each other to make sure everything looks good. Okay, so here's the plots. First, lift coefficient versus angle of attack. The blue is the experimental data. The red is what I got in CFD, and not surprisingly, it agrees very well. I don't need nearly as fine a mesh to get good resolution and lift. Second is drag. So I did in two cases. These dots here, the blue and the green, that's experimental data, and the red and purple is my CFD data. So the red here is with the transition. You can see that agrees very well. Purple here, it's a little under predicting, though probably within experimental error. Partly, I suspect the difference here is that the experiment, because it's tripping the boundary layer on purpose, to get fully turbulent flow, that adds some drag of its own. And so I'm not quite capturing that in the CFD. So, but this is quite good. I didn't do a full grid convergence study, so I may be able to do better, but it's doing quite well in terms of prediction. Okay, so I'm leveling out here, but I'm going to let that go, and I think, this will be good for the video.